Okay, good morning. Today, what I'm going to do is I'm going to continue this discussion from chapter 8, which I started at the end of the last discussion. And what we're going to do today is we're going to look at covalent bonding, which is section 8.2. Now, covalent bonding is probably one of the more significant developments of the 20th century in terms of chemistry because it gives us an explanation, a model, a theory to work on that has some validity to explain the behaviors of molecules from the smallest ones like dihydrogen and water up to the largest ones, proteins and nucleic acids and such. So let's begin by, again, considering this idea of the valence electrons. So when we consider an atom, I'm going to pick sodium. We won't work much with sodium in this chapter, but we'll pick sodium. If we consider the electron configuration according to the rules of quantum mechanics, we end up with what's called a ground state configuration, a ground state electron configuration that looks something like this. There's 11 electrons in a sodium atom. The Aufbau principle suggests that the electrons will occupy the lowest available orbitals, lowest energy orbitals. The Pauli exclusion principle suggests that a maximum of 2 electrons can occupy an atomic orbital at any given time. And so we end up with a configuration that involves multiple orbitals with, in general, pairs of electrons, right? Spin up, spin down. And so this is the ground state configuration for sodium. So it is useful to identify the highest value of the principal quantum number, in this case, n equals 3, and to consider those electrons as different from the other electrons. They are further away from the nucleus, closer to any other atoms. The further away you are from the nucleus, the closer you are to other atoms. So they're closer to other atoms. And very often they exist as individual electrons, not pairs of electrons, but only one electron. So in the case of sodium, we're going to call this electron and that orbital, we're going to call it the valence shell, n equals 3. And that electron in there is going to be called a valence electron. So we represent that valence electron, not the core. These are all core electrons here. We're going to represent that valence electron with just a single dot. Okay. And we're going to argue that that electron is essentially, or that shell, is the shell that will be available for forming bonds with other atoms. So for example, if I were to take a hydrogen atom, which is 1s1, right? There's only one electron. So this is our valence shell. And there's one valence electron. And then I take another hydrogen atom. So I'm gonna letter them A for hydrogen A, B for hydrogen B, 2 of them, right? I don't want to put numbers as subscripts because there's so many numbers here to begin with. Same thing, it's 1s1, right? Each hydrogen atom is 1s1 in its ground state. So we can represent this in the following way. We draw the Lewis dot symbol for each hydrogen. Now I'm going to draw them so that the valence electron for each atom is pointing toward the other atom. Okay, so each of those valence electrons is pointing toward the other. And what we'll claim is that because of quantum mechanics, because of the potential to have pairs of electrons occupying orbitals, right? That's a real phenomenon. That what can happen is these 2 hydrogen electrons can form a pair of electrons. And that pair, we represent them with 2 dots. Okay, see how they're represented with 2 dots? They're actually in the same orbital. I'm not going to talk about the orbital right now. One is spin up, the other one is spin down, so it obeys the Pauli exclusion principle. But now these two electrons are connected to both nuclei. Remember, that symbol is really, in a sense, it's the nucleus, right? The symbol represents the nucleus. The valence electrons are represented with dots. So those two nuclei, those two hydrogen atoms, if you want to call them that, they are attached to each other in a sense by these two electrons. Now remember, the electron's negatively charged, right? So the nucleus of the hydrogen atom is positive. You've got these two negative charges, and then you got another positive. You know, that's the nucleus of the first hydrogen. That's the nucleus of the second hydrogen. And then you've got these two negatively charged electrons. Now, they should repel each other, except that the Pauli exclusion principle allows for two electrons to occupy the same region of space as long as they have opposite spins. So the effect of this is the two electrons hold the two nuclei together. The nuclei don't fly apart because they're positively charged. They're held together almost like a glue with these two electrons. Okay. Now, this Lewis dot structure here that I've shown here for this molecule of H2 uses dots. Most in this section 8.2, most of the problems, they show you dots. But I do want to point out that the convention in today is that we generally don't show bonding electrons as dots. We show them as lines. This is called line notation. So this is a sort of dot notation. And then this is a line notation. This is the more standard method for representing these arrangements of electrons. Okay. Now, let me show you another one. In this case, I'm going to take oxygen. And again, I'm going to take two oxygen atoms. Actually, you know what? Let's not do oxygen. Let's do fluorine. Fluorine's easier. Okay, Fa and then Fb, two fluorine atoms. We do know that fluorine is one of the diatomic elements, right? It exists as individual molecules, F2. So fluorine is element number 9, so it's 1s2, 2s2, 2p5, right? Same thing. Each one is 1s2, 2s2, 2p5. This is the valence shell right here, right? A lot of valence electrons, 7 valence electrons. Now I'm going to draw the Lewis dot symbols for each of them. So here's the first one, A. 1, 2, 3, 4, 5, 6, 7. So notice there's one electron all by itself. That's an unpaired electron spin up. Most likely spin, could be spin up, could be spin down, but does not have another electron with an opposite spin. So this is paramagnetic. Now let's do the second one. Well, it's going to be the same, right? 1, 2, 3, 4, 5, 6, and 7. Now what I'm going to do is I'm going to rotate them. I'm going to rotate the electrons so that the one electron, the unpaired electron, is pointing toward the other atom. Okay, so all I'm doing is I'm just rotating them around this way. Same thing here. I'm going to rotate them around because we want to have those unpaired electrons pointing toward each other, just like we had in the hydrogen. Okay, now look what happens. You have unpaired electron, unpaired electron. Those two can go into the same orbital. Be spin up, be spin down. And now you got a chemical bond, right? So in fact, what we end up with is a chemical bond. So I'm going to represent it that way. And then notice you have all these other electrons that are not bonded to the other atom, unlike hydrogen, right? Because hydrogen only has one electron. This one has 7, right? Again, we're only concerned with the valence electrons, not the core electrons. So what we notice in nature is that a lot of molecules, particularly the nonmetals, tend to form arrangements similar to this, where a pair of electrons are bonded together, not bonded together, but form a bond to hold the nuclei together. And there are these other electrons in the valence shell that are not bonded to the other atom, and we call these lone pairs. So each of these is called a lone pair. Lone because it's all alone, it's not bonded to the other atom. So in this case, each atom has 3 lone pairs, right? 1, 2, 3. Each atom has 3 lone pairs, and this we're going to call a bonding pair because it's holding those 2 nuclei together. Again, remember the electron is negatively charged, so it has an electrostatic attraction for the protons that are in the nuclei of each of these atoms, so it will hold these 2 nuclei together. It is not a rigid structure, it vibrates. The nuclei are kind of trying to push themselves away from each other. The electrons are trying to hold them together, so it will undergo some sort of dynamic vibration. Okay, that's a study that we can do. We can study these vibrations. Okay, again, like I said, this notation is somewhat outdated. Most chemists will use this notation. You represent the bonding pair with a line. And this is called line notation. More standard, more accepted today than these dots. Another thing to notice is that if you count up all the electrons, all the valence electrons around each atom, so remember each one had 7 to begin with, but by sharing an electron, a pair of electrons, the 2 atoms now have increased the number of electrons around them by 1, right? So each one had 7, but now there's 2 that are shared. So each now has 8. And so we call that the octet rule. And this is very common in nonmetals. It's called the octet rule, which is for nonmetals. This is where we share electrons to give each atom a total of 8 valence electrons. Seems to be a pattern. Okay, seems to be common. It is common. This is commonly observed. It's not observed in hydrogen because hydrogen only has 1 electron. So hydrogen, so this is for the nonmetals. Hydrogen has its own rule, which is called the duet rule. 2 valence electrons. Which we just saw, right? Whether you use the dot notation or the line notation, 2 electrons, okay? So nonmetals tend to have 8. Now there are exceptions to that, or arguably there are exceptions to that, but generally it works relatively well. So, you know, what happens is, if you think about it, let's take oxygen. Well, let me make a new slide here. If you take oxygen, for example, 1s2, 2s2, 2p, 6, wait a minute, I'm doing something wrong here, 2p4, right? Oxygen is element number 8, so it has 8 electrons, and then it has 6 valence electrons. Okay, so what happens is if you do the Lewis dot symbol for oxygen, 1, 2, 3, 4, 5, 6, so I'm going to stop right there. See how it's 2 short of 8? If it had 2 more, it would have 8. So 6 is what it has. It needs another 2 to get up to this octet. It needs 2 more. So what does it do? It very often will form a bond to 2 separate atoms or 2 bonds to a different atom. So what you'll see is the oxygen will use one of these electrons to form a bond to a hydrogen atom. Sorry. Right? So the hydrogen is providing one of them, the oxygen is providing the other. Same thing over here, a hydrogen atom will provide 1 electron and the oxygen provides the other, and then it'll have 2 lone pairs. There's your water, that's H2O, right? So you have a total of 2, 4, 6, 8 electrons for the oxygen, and then each hydrogen has 2. Okay, so we would maybe draw this using line notation like that. So what would we say? We say the oxygen has 2 lone pairs. The hydrogen doesn't have any lone pairs, but they're 2 bonding pairs. Each atom has at least 1, right? The oxygen has 2 bonding pairs. The hydrogens have 1 each. Okay, this is for oxygen. Okay, so there's all that notation right there. Okay, that's the terminology. So what you'll see is that if you go into the periodic table, there's a tendency then, so here's helium over here. This is often referred to as group 8A, even though helium only has 2 electrons. Beneath that is neon, argon, krypton, and xenon. If you count the number of valence electrons, with the exception of helium, they all have 8 valence electrons, which is kind of cool. Now you go over to the next column, which is fluorine, chlorine, bromine, and iodine. They all have 7 valence electrons. And then you come over to 6A, which is oxygen, sulfur, selenium, and tellurium. They all have 6 valence electrons. Come over to 5A. You got nitrogen, phosphorus, I almost put arsenic, and then what's the one that comes underneath arsenic is antimony, and then bismuth is behind that, below that, but I'm gonna leave that one. 4A is your carbon, silicon, germanium, and tin. Okay, and then let's go one more, 3A, which is boron, aluminum, gallium, and indium. Okay, so those are nonmetals, right? I'm just focusing on the nonmetals right over here. Now you can, of course, you could do 1A and do hydrogen. So mainly we're going to focus on nonmetals. So that's the P block, right? Yesterday I called that the P block. There's 6 columns in the P block. Okay. So think about it this way. This number here is telling you how many valence electrons they have. So that's very nice. This one already has 8 with the exception of helium. So let me draw a little circle around helium. 8, 8, 8, 8. So they don't need to form any bonds. So they're not going to form a bond with any other atom. There are ways to get krypton and xenon to react, but they're very unstable. These ones, these elements, the halogens, group 7A, they need 1 more electron to get up to 8. So they will tend to form 1 bond to 1 atom, right? If you have 7 electrons and you just need 1 more, you're going to form a bond to one other atom. So you're going to see molecules where you have 1 bond with fluorine, right? HF, for example, or HCl, chlorine's right below it. Because they already have 7, so they just need 1 more to get up to 8. Okay, or Cl2. They already have 7, so give them 1 more and they got 8. So you have 1 bond between the 2 atoms. Of course, hydrogen is the same way, right? Because hydrogen has 1 electron, it needs 1 more for the duet rule. Then you come over to 6A. Oxygen has 6 valence electrons. So what does it need? It needs, I'm just going to draw these in real quick. It needs 2 more electrons. So what does it do? It needs 2 bonds. Each other atom provides an electron. So it could have 1 bond to 2 different atoms, like H2O, or it could form 2 bonds with 1 other atom. So for example, O2 is 2 pairs of electrons shared by each atom. See how I drew that one? 2 pairs are shared, 2 bonding pairs. So again, using the line notation, we would draw those like this. Okay. So you notice then this one needs 1 bond, this one needs 2 bonds, this one needs 3, this one needs 4. Now you might say, well, what about this one? This one needs 5. Well, no, it turns out that these ones will behave a little bit differently. Okay. And so they do not tend to form 5 bonds. We'll have to deal with them a little bit separately. They tend to form 3 bonds, as it turns out. But these ones, 4 bonds, 3 bonds, 2 bonds, 1 bond, and 0 bonds, if you want to put it that way. That's why they're chemically inert. Okay. All right. So let's start taking a look then. That's pretty much all of the background for this section. Let's take a look at some of the problems. Got plenty of time to do that. Okay, counting bonds and non-bonding electron pairs in Lewis structures. Below is the Lewis structure for the chloroform CHCl3 molecule. So this is a Lewis structure. Notice they're using the dot notation. Again, most chemists will not use this notation. They will use the line notation. So anywhere that you see a pair of dots in between 2 atoms, 2 symbols, that we would represent with a straight line. If there's 2 pairs, we'd have 2 lines. And if there were 3 pairs, we'd have 3 lines. So count the number of bonding pairs and the number of lone pairs around the bottom chlorine atom. So read these very carefully, the bottom chlorine atom. So just this one down here. So this chlorine atom right here has a pair to the carbon. So that's 1 bonding pair. And then it has 3 pairs around it that are all by themselves, right? They're not connected to any other atom. So 3 lone pairs. So 1 and 3 bonding in lone pairs. Each chlorine essentially has the same situation, right? Each one of them has a bonding pair and 3 lone pairs. Notice if you go through it, you'll find that all the electrons around the hydrogen are 2. All the electrons around each of the chlorines is 8, and all the electrons around each carbon, there's only 1 carbon, around the carbon is also 8. So the octet rule, 8 electrons, 8 valence electrons around each non-metal seems to be in force here. Let's take a look at another example. This one's a lot simpler, right? This one is CH4. Look at, there's around the carbon. I know it's going to, oh, actually, I take it back. I thought I was going to ask about the carbon. Count the number of bonding pairs and the number of lone pairs around the right hydrogen atom. Well, here's the hydrogen atom on the right. It only has 1 bonding pair, no lone pairs, which is what we would expect, right? If it's going to be in a molecule, it's got to have at least 1 bond to another atom. Otherwise, it wouldn't be a molecule. And it has the duet rule, so it doesn't generally have more than 2 electrons. Okay, let's see if there's one that's any different. Here's a water molecule. Count the number of bonding pairs and number of lone pairs around the oxygen. Okay, there's your oxygen. So it has 2 lone pairs here and then 2 bonding pairs. Okay, looks good. Now here's an ion. This is an anion, counting the electron pairs in those structures with double or triple bonds. So notice we can have more than 1 bond between atoms. It's very common. Oxygen, very common for it to have 2 bonds. Nitrogen, very common for it to have 3. Carbon's pretty cool. It can have 1 bond, 2 bonds, or 3 bonds to 1 different atom. And we call those double and triple bonds. A double bond is when you have 2 pairs of electrons between 2 atoms. A triple bond is when you have 3 pairs of electrons between 2 atoms. So count the number of bonding pairs and lone pairs of a hydrogen atom. There's only 1 hydrogen in here. Well, that's pretty simple, right? Notice they do put the bracket notation here. If you're doing an ion, so if something is plus or negative, when you draw these Lewis structures, you want to put square brackets around the structure, and then you put the charge outside so that we know that in this case, it's not HCO3, it's HCO3 minus the bicarbonate ion, okay? Hydrogen carbonate is called. So the hydrogen, again, that's pretty simple. The hydrogen just has 1 pair, it's a bonding pair. That's kind of silly. Let's take a look at another one. Okay, so notice this one. This is called a triple bond. There's 3 pairs of electrons holding the 2 nitrogen atoms. Why? Nitrogen is in group 5A. It has 5 valence electrons. It needs 3 more. By doing 3 bonds, that gives it 8 electrons. This one's neutral. It's not an ion, so it doesn't have brackets around it with a charge. Count the number of bonding pairs and number of lone pairs around the left nitrogen atom. So this one over here on the left. Well, there's 1 lone pair, and then there's 3 bonding pairs. Okay, so there you go. That's the counting of pairs of electrons. Deciding whether a Lewis structure satisfies the octet rule. Now remember, the octet rule is 8, right? So now what we do is we look for hydrogen, it's the duet rule. For the nonmetals, it's the octet rule, okay? So let's take a look at the first one. Here's an HBr molecule. There's something wrong with this, but let's take a look at it. The hydrogen has 4 electrons. That's not good. So is it reasonable? I would say no. Because the hydrogen has 4 electrons. The hydrogen is the duet rule, should have 2. Okay. And so what about bromine? Bromine should have 8. It's a nonmetal. So 2, 4, 6, 8. Remember, each line is 2 electrons. We're now replacing the pairs, the bonding pairs, with a line. So if you see 2 lines, that's two pairs. That's 4 electrons. So the bromine has 8. That's not a problem. But the hydrogen has 4. So does it have the right number of valence electrons? Well, we should look at that too. How do you determine that, whether it has the right number of valence electrons? That's pretty simple. What you do is you say, okay, hydrogen is in group 1A, it has 1. Bromine is in group 7A, so it has 7. We went over that. So that's 8. So it should have 8 total. It does have 8 total, so that's not a problem. There's 2, there's 4, there's 6, there's 8, right? So you're looking at the periodic table. Make sure you have that handy for you to count the number of valence electrons. Bromine is a halogen over here, 7 valence electrons. Hydrogen is over here, 1 valence electron. 1 plus 7 is 8. It has 8 electrons in this Lewis structure. So that's not a problem. It's not, no, it has the wrong number of valence electron, and the correct number is, whatever. That's not the problem. It has the right number of valence electrons, but it doesn't satisfy the octet rule. Well, that's actually not true either. The symbol for the problem atom is just hydrogen. It's just H. So it's not a problem of the octet rule. It's really just a problem for hydrogen. So let me look at the explanation here for this one. What do they say? Okay, let's look at the HBr. The HBr molecule has 8 valence electrons. So does the Lewis structure. So that's good. Now count the valence electrons. So there's 4 pairs around the bromine. That's fine. There's 2 pairs around the hydrogen. The octet rule requires 1. Okay, so this is a flaw in the ALEKS programming with hydrogen. What it should do is it should say the problem is that hydrogen needs to follow the duet rule, right? Not the octet rule, because there's no 4 electron rule. There's a 2 electron rule for hydrogen. So what they want you to do is they want you to say it's a failure of the octet rule, and that the problem element is hydrogen. So just type in an H, but that's incorrect. It's not a problem with the octet rule. It's a problem with the duet rule for hydrogen. They just didn't put in the correct possibility here. They didn't add a 3rd possibility, which is the duet rule. So I guess just if it's a problem with the hydrogen, just put in the octet rule and then put the symbol for hydrogen. Okay. Let's take a look at the second one here. Okay, well, let's count up electrons first of all. Hydrogen is in group 1A, so that's 1A, that's 2, 3. So each hydrogen has 1 valence electron, that's 3. Oxygen is in group 6A, so that's 6. So 6 plus 3 is 9. But look at this charge. Remember the brackets? We use the brackets when there's an ion. Plus means you've lost an electron. If you lose one of your 9 electrons, you now have 8. So we do have 8 electrons total, okay? Now, let's go through each hydrogen. Hydrogen 2, duet rule, 2, duet rule, 2, duet rule. Excellent, hydrogen is set. What about oxygen? 2, 4, 6, 8. 8 electrons, octet rule, we're set. This structure is a yes, it is reasonable. The oxygen has 8, the hydrogen has 2, each hydrogen has 2, and it has the total number of electrons, right? Don't forget to subtract 1 electron when you see that plus. Here's carbon monoxide. This one might be okay. Let's see. Carbon is in group 4A, so it's got 4. Oxygen is in 6A, it's got 6, so that's a total of 10. So it should have 10. 2, 4, 6, 8, 10, 12. Nope. Has the wrong number of valence electrons. When students draw Lewis structures, this is a very common mistake to just draw in enough dots and bonds so that everything has 8. And that's not how it works. You cannot change the physics of the atom. The atom has a certain number of electrons, a certain number of valence electrons. You have to go by this chart. Carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8, hydrogen 1, of course, right? So no, wrong number of valence electrons for this one down here, okay? So there's 3. Let's take a look. Well, I'm not going to do a whole bunch more, but let me do another one. Let's look at this first one here. Okay, N2. Now think about it. Remember what I said about nitrogen? It's in group 5A. So it's probably going to need 3 bonds to get up to 8. It's got 5, needs 3 bonds to get up to 8. So the fact that there's only 1 bond there could be a sign or something wrong. So what do? You first say, okay, this is nitrogen, 5 valence electrons. It's in group 5A. This is nitrogen. It's also in group 5A. So that's a total of 10 electrons. So does it have 10? 2, 4, 6, 8, 10. Good. So it does have the correct number of valence electrons, but that doesn't mean it's a good Lewis structure, right? We have to also determine whether we've got the octet rule. And look at that. Neither atom has 8 electrons. This nitrogen on the left has 2, 4, 6. This nitrogen on the right has 2, 4, 6. So the symbol is N. It does have the correct number of valence electrons, but it doesn't satisfy the octet rule for nitrogen. I don't think you have to put N comma N, do you? Let me write. I'm going to look at the explanation just to be careful. Well, they're both. So I'm not sure whether you have to put N comma N or just N, to be honest with you. I would have to actually go through it. So if you're having a problem with that one, it might be that you have to put it twice, N comma N, as opposed to just N. Okay, let's look at the second one here. This is the azide ion. Again, nitrogen 5A, so 5, 10, 15, but now it's negative. Most of the stable structures, or most of the structures you're going to see, have an even number of electrons. There are some that have an odd, but mostly they have an even number of electrons. So that's why these ions, partially why these ions form. It gives them an extra electron or removes an electron to make it an even number. So 5, 10, 15, but you got this negative that adds an extra, so it's 16. If it was -2, you would add 2. If it was -3, you would add 3. So there's 16 valence electrons. So does it have 16? 2, 4, 6, 8, 10, 12, 14, 16. Good. Correct number of electrons. Now we check for the octet rule for all of these nitrogen atoms. This atom on the left has 8, no problem. This atom in the center has 8, no problem. This atom on the right, oh, no, no good. This atom on the right only has 6 electrons there, so no, it has the correct number of electrons, valence electrons, but it doesn't satisfy the octet rule for N. Last one, carbon monoxide. This looks like we got the octet. This is one we just looked at, right? This is when we looked at carbon monoxide. It didn't have the correct number of electrons. It needed to have 10, but this one had 12. So even though it's the octet rule for each one, it's okay. It didn't have the correct number. Okay. Oh, actually, it says it. For example, if two oxygens don't satisfy it, you enter O, comma O. All right. It's more than one. Okay. All right. Good. Let's take a look at a different one. Predicting the single bonded molecular compounds formed by two elements. For each row in the table below, decide whether the pair of elements will form a molecular compound held together by covalent chemical bonds. If the elements will form a molecular compound, check the box and enter the chemical formula and name of the compound. If the elements will form more than one molecular compound, use the compound with the fewest total number of atoms. You may assume that all chemical bonds are single, not double or triple. Okay, that's useful. Okay. All right, well, let's take a look at the first one. The first one right here is an ionic compound. How do I know that's an ionic compound? It's a metal. Sodium is a metal, right? Remember, the metals are over here. The non-metals are over there. So if you have an element over here with an element over here, metal, non-metal, that's an ionic compound. Okay. If you have two elements that are both non-metals, that's called a molecular compound. So sodium oxide is a ionic compound. The element pair will form a molecular compound. Well, no, it's not going to form a molecular compound because it's a metal with a non-metal. So no, you just say no. And if the element will form more one, okay, right? So there is no molecular compound there. Okay. Second one, nitrogen and fluorine. Okay, nitrogen is a non-metal over here. Fluorine is a non-metal over there. That's a molecular compound. Okay. Now here's how you go about it. You've got nitrogen needs 3 bonds, right? It's in group 5A, so it needs 3 bonds. Fluorine only needs 1. So fluorine is just going to form a bond to one other atom. But what about the nitrogen? The nitrogen needs to form a bond with 3 different atoms. Okay. So how's that going to happen? Well, if nitrogen needs 3 atoms and fluorine only needs 1, then you're going to have 3 fluorines and 1 nitrogen. Let me show you a picture of that just so that you can see it. So nitrogen needs 3 bonds. Again, because it's in group 5A. Fluorine is in group 7A, so only needs 1 bond. So how is that going to work out? What's going to happen is the nitrogen needs 3 of the fluorines. And each fluorine only needs 1. Now, I'm not drawing out the whole Lewis structure. I'm not drawing in the lone pairs. We don't need that. This problem is not asking us to do that. All it's asking us is to figure out what the formula is going to be, right? So if you need, now again, why 3 bonds? Because it's in group 5A, it needs 3 more electrons. By having 3 bonds here, 3 different fluorine atoms, that's going to give it a total of 8. Okay, 5 plus 3 is 8. But each fluorine only needs 1 bond. So the only mathematically, the way that's going to work out is you're going to get this. You're going to get each fluorine has 1 bond. Each nitrogen has 3. So that works out as NF3. And how do you name these? You name the first element, nitrogen, right? Then you name the third one, but use those prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, going from 1 to 10. Okay, and then you change the second element's ending to IDE. So nitrogen becomes nitride. So this would be called nitrogen tri because there's 3 fluoride, right? Remember, you change the second element to IDE. Use the prefix for it, and then you change the ending to IDE. So this would be nitrogen trifluoride, and that would be your name. So your chemical formula, NF3, and then the name would be nitrogen trifluoride. Let's take a look at the third one. So the third one has hydrogen and chlorine. Well, this one's pretty straightforward. Hydrogen, consider it a nonmetal, even though it's on the metal side. Chlorine is a nonmetal. So this would be a molecular compound. Yes, it will form a molecular compound. Hydrogen needs 1 electron, right, to get up to 2. So that means it's going to form 1 bond. So that really means it just needs 1 other atom. The chlorine is in group 7A, which means that it has 7 valence electrons. It only needs 1 more electron, so it only needs 1 bond. So each atom only needs 1 bond, so they only need 1 other atom. So this would be a molecular compound. If each one only needs 1, it's just 1 and 1, so it's HCl. So this would be HCl. And then the name would be, from a molecular perspective, it would be called hydrogen chloride, right? Hydrogen chloride. You might say, oh, why aren't we following the hydrogen monochloride? Well, for these hydrogen compounds, we just generally don't. So it's hydrogen chloride. If it's dissolved in water, it's called hydrochloric acid. But if it's a molecular compound, a pure compound, it's hydrogen chloride. Okay. Let's take a look at another one. Okay, sulfur and bromine. Okay, sulfur, group 6A. So that is definitely a nonmetal. Bromine, group 7A, that's a nonmetal. So they both are nonmetals. That's a molecular compound. Magnesium bromide, Mg. Well, that's a metal, and bromine, that's a nonmetal. That's an ionic compound. So second one, you're not going to do anything because it's an ionic compound. Third one is hydrogen and fluorine. Okay, well, again, hydrogen and fluorine, that's a molecular compound. So the first and third are molecular compounds. Okay, sulfur is in group 6A. So it needs two more electrons. So it needs 2 bonds. So whatever, it's going to need 2 other atoms. The bromine is in group 7A. So it only needs 1 other atom. So it just needs 1. So here's what will happen with that one. Okay, you got sulfur, it needs 2. Bromine only needs 1. So how does that work out? It works out with each bromine being attached to the same sulfur, right? So this one gives the sulfur 2 and it gives the bromine 1. Okay, so that's SBr2. In general, when you write the formula, the one where there's only 1 atom, you write that one first, that symbol first, and the one where there's more than 1, 1, 2, 3, or 4, you write that one second. So how do we name it? Sulfur. Second one gets changed to IDE, and there's 2 of them, so dibromide. Okay. And then the last one in that set was hydrogen fluoride. Hydrogen just needs 1, fluorine just needs 1, so it's just that, so it's just hydrogen fluoride. Not monofluoride, just fluoride for hydrogen, for the hydrogen compounds. If it were BRF, then it would be bromine monofluoride. Okay, but if it's hydrogen, you don't use the prefix. Okay, in general, anyways. All right, so there's that one. Let's see what else we got. Predicting the compound formed by 2 main group elements. Kind of pretty much the same thing, right? It's pretty much, they're not having you name it. They're just having you determine whether it's ionic, molecular, or neither. Now this is interesting that neither, what would be neither? Well, let's go through it. Okay, the first one has nitrogen, non-metal, chlorine, non-metal. So that's molecular. Okay, molecular compounds are nonmetals. And then same thing, nitrogen, how many electrons does it need? Chlorine, how many electrons does it need? The nitrogen needs 3, so it's going to bond to 3 other atoms. The chlorine is in group 7A, it only needs 1 electron, it's going to bond to 1. Okay, so it's pretty much the same idea as the previous one. You're going to write the formula, you don't have to give the name to it. But I do want to draw your attention to the middle one here. This is an interesting one. This is a noble gas. Radon is a noble gas. and argon is a noble gas. So in general, what we do is we would claim that noble gases don't form compounds. Okay, so neither. It's not going to be an ionic. It's not going to be a molecular. It's going to be neither. Okay. Okay. Pretty much the same idea. Okay, that's good. Okay, I want to show you this one. This is the last one in the problem set. Predicting the relative length and energy of chemical bonds. And this is an interesting topic. And what I want to do, I'm not allowed to click these, but that's okay. So let me talk about it a little bit. The idea of bond length and bond energy. Okay. Bond energy is generally, the symbol for that is delta H. And the bond length is, the symbol for that is an R. Okay. So the idea here is, let's imagine that our atoms are essentially spheres. That's essentially what they are. They're like little balls. So here's an atom. And let's suggest that it's bonded to another atom. Sorry, that's not a very good looking sphere or circle. Okay, so let's say there's a chemical bond here. Okay, so I'm representing it differently than I have before, right? So for example, let's say this is H2. We could represent it this way too, right? And we could represent it this way. There's many different ways we can represent these. So I'm representing this over here a little bit differently. Okay, the two atoms are attached to each other. It turns out that there are ways to measure how close the nuclei are. I'm going to put the nucleus of each atom right there. Okay, so there's your nucleus for each atom. There are ways, X-ray diffraction is the main one, to determine how far apart, what the distance is, the bond length, we call it, between those two nuclei. Okay, so it's a measure essentially how big the molecule is, but also how big the bond is. What is observed in general is that as you add more electrons, more bonding electrons between two atoms, the two nuclei tend to be drawn closer to each other, and the strength of that bond increases. So as more bonds are added to a pair of atoms, the bond length tends to decrease, and the bond energy tends to increase. Okay. Now, why is that? Well, one way of thinking of it is, again, thinking of the pair of electrons that are holding two atoms together as a sort of glue. It's pulling, they're pulling the nuclei apart, toward each other. So as you add more bonding electrons, those nuclei will have a tendency to get closer to each other. Okay, so if they get closer to each other, then this distance R decreases, right? So they're getting closer. So the bond length decreases. That means they're closer together. Now, in terms of energy, what happens is more electrons holding the nuclei together means that if you want to break the bonds between the atoms, you have to break all those pairs of electrons. So if you have more pairs of electrons, they're going to hold those two nuclei together even more tightly. So 2 pairs is stronger than 1 pair, and 3 pairs is stronger than 2. So bond energy or bond enthalpy tends to increase with the number of bonds, and bond length tends to decrease. Okay, that's in general what we observe. We're going to talk more about bond energy or bond enthalpy. Is the last topic of this particular chapter. We won't talk too much about bond length. We'll talk a little bit about it when we get into electronegativity. Okay. So let me take a look then. Let's look at the example. I may have to show the answer just to see what, I don't know what the options are giving me. So predicting the relative length, so that's the bond length, and the bond energy of a chemical bond. Which of the highlighted chemical bonds in the molecules is the longest? Which one's the shortest? Which one's in between? Which highlighted bond requires the highest energy to break? Which one requires the lowest? And then in between. So actually, it looks like we're comparing these 3 different structures here. Now, I can't actually see. Oh, there it is. Okay, so there's the highlighted bond right there. So you see there's a highlighted bond right there, a highlighted bond right there, and a highlighted bond right there. So really what we're doing is we're comparing this bond to this bond to this bond. Okay. So what about bond length? So this is actually a little bit different than when I was just describing. I was describing the difference between single and double and triple bonds, really, the number of bonds between 2 atoms. This is actually asking something different. This is asking us the size based on changing what atom is in the structure. Okay, so it's a simple explanation. What happens is, we haven't covered this, but hopefully we'll have a chance to cover it. As you move down the periodic table within a family, so for example, the halogens in group 7A are a family: fluorine, chlorine, bromine, iodine. The size of the atom increases because it has more electrons. As you add more electrons, it gets bigger. Okay, so the iodine is larger than a bromine, the bromine is larger than a chlorine, and a chlorine is larger than a fluorine. Okay, so let me show you what I mean by this. So we're going to talk about atomic size, which is generally referred to as radius, the atomic radius. What's observed is that within a family, remember the family is the same column. A period is the row, but a column is a family or a group. Okay, gets larger in that direction. Okay, so iodine is the largest of these 4, and then fluorine would be the smallest. Okay, and that holds for other columns as well. So for example, nitrogen in 5A, phosphorus, arsenic, antimony. This one would be the largest of the 4, and this one would be the smallest. Very simple. Now that has an effect in terms of a bond. If I have a carbon atom, and then I bond that to, let's say, a fluorine, the fluorine is the smallest of the halogens, right? It's the one at the top, so it's the smallest of those 4. But now if I take the carbon and I bond it to an iodine, the iodine is larger, right? It's the largest of the 4 down there at the bottom. So the bond length R, okay, well, actually we'll call it the bond length. Let's just call it the bond length. Let's not use a symbol. You can kind of tell, right? Which one has, the longest bond length. Which one's the largest? It's going to be the CI, right? It's going to be the one with the largest atoms in it. So in general, this problem is actually pretty simple to solve, because all you got to do is look for the one that has the largest atom. That'll be the longest bond length. And the one that's the smallest atom will be the shortest, right? So this would be shorter. The bond length would be shorter. And this would be longer. Okay, so that's pretty straightforward. And then if it's an element in between, if it's chlorine or bromine, this is going to be in between. Okay, so that's actually relatively simple. The energy is a more interesting issue. We'll talk about energy in a moment. Okay, so let's take a look. So notice I didn't really read it very carefully. It's carbon to bromine, carbon to fluorine, and carbon to chlorine. Fluorine is the smallest of the halogens. So that's going to be the smallest bond, the shortest bond. Of the three, bromine is the largest atom. It's element number 35. So this is going to be the longest bond. Longest, shortest, and then this one will be in between. And that's all you have to say with that. Now, what about the energy? Well, it turns out the further away the atoms are, the weaker the bond. And the closer they are together, the stronger the bond. Okay, so what that means is the bond energy, it does the reverse of the bond length. As the bond gets bigger, longer bond length, the energy gets weaker. So this one right here had the longest bond length. This one's going to have the smallest energy. It's going to be the lowest energy. This will be the weakest. And this one right here, this one was the shortest. That's going to be the strongest. So that'll be the strongest bond. And that's all you got to do with that. You just have to determine whether it's the strongest, the weakest, or in between. Here's another example. Okay, now this comes back to what I was talking about, I guess. Is that right? You got a triple bond. So now they're not comparing different types of atoms like fluorine, chlorine, bromine, and iodine. They're comparing the same atoms, but with just different numbers of bonds. So a triple bond would be the shortest, more electrons holding it together, so it's closer. So this will be the shortest. But again, the shorter the bond, the stronger the bond. So this will be the highest energy. This one right here is a double bond. This one's a single. Well, the single, it has the fewest electrons holding it together, so that'll be the weakest bond. But it'll also be the longest. So longest and weakest. And then 2 is in between, right? So it'll be in between for both of them. Okay. So really, there's two concepts, two very different concepts that particular problem is going to hit you with. One is what happens if you change the sizes of the atoms, use different elements, fluorine, chlorine, bromine, and iodine. The other one is what if you think you have the same element, nitrogen in this case, but you change the number of bonds. Okay, so those are, you know, they're related, but they're different issues. More bonds is a stronger bond, and shorter bond. And then the larger the atom is going to be a longer bond, and the weaker the bond. Okay. So there you go. So that is it. That's all of the problems from that section 2. So what we're going to do tomorrow is I'm going to start looking. Let me stop share there. Let me come back to Alex. Is we're going to start on section on electronegativity and polarity. I think I misstated the section that we were looking at. So let me show you here just so that you can see it. I misstated it at the beginning. I sometimes get these sections mixed up. There we go. So yesterday we did Lewis dot symbols. So those were all the problems we did yesterday. Today we did covalent bonding. I thought that was 8.2, but I'm sorry, it's 8.3. 8.2 is ionic bonding, which we're not covering in here. So 8.3, we did all of these problems here. Tomorrow, I'm sorry, is 8.4. Okay, so 8.4 is electronegativity and polarity. That's a, you know, there's only a couple of problems you have to do there, but it's pretty deep conversation about how we do that. So we'll cover that tomorrow. If there is some time, we'll start drawing Lewis structures, which is 8.5. But I'm not sure that we'll see. We'll see how it works out. We might be able to do a little bit of that. And then you can see there's a lot of sections in here. We got to go through Lewis structures and formal charge. Then we got to do resonance. Then we got to do exceptions to the octet rule. And then we got to do bond enthalpy. So there's a lot in this chapter. This is a really important chapter for those of you. It's probably the most important chapter for those of you that are going to go on to take organic chemistry. So if you're doing any of these programs, like you're going to go to Hunter College as a biology major, or City College, or Stony Brook. Or if you're doing any of the medical professions like MD, RN, you may not need to do it. It's hard to say. But certainly MD or pharmacy or dental, you got to take organic chemistry. Chapter 8 is probably the most important chapter because it's the basis for the whole discussion of how you draw organic molecules as Lewis structures. So we're going to go through this really kind of in detail, spend some time on it. This is all chemistry that we're doing in here. Chapter 8 is chemistry. And we do want to have time to get into chapter 9 as well, because chapter 9 is more advanced topics in chemical bonding. We'll do that as well. Okay, so have a great day and enjoy.